Hey, this is Steven from Legit Tech Tutorials and the Green Engineers, and welcome back to DIY Metal Mill. I believe this is episode 3, so we're going to continue looking at some of these things to kind of finalize a lot of these different things that we're going to do. So again, remember that the reason why we're going with the Trello, why we're going with the VMC idea, why we're going to check in on the VMC idea compared to basically the what's the word I'm looking for? One second, let me log into instead of the metal router, is that we get something a little bit more robust machine, and we could do a little bit more things with it that will be pretty interesting. So basically, again, the issue with the VMC versus a regular router is that you lose a lot of the travels, because basically the machine has to have half go on one side and half go on the other side. So I measured this hole that this is now going to sit in, because I'm going to use one machine. I could give it more space. So there is this edge. So let's go ahead and do. So basically there's this hole on the other side of my cabinet. It's usually where we store some big material. So that's where probably the bamboo for the EcoBase 3D printer is going to be stored. It's for big long material storage. So but that can be moved. There's another place where it could be stored near the door that I actually like a little bit better, because there's not a whole lot of room there, and it's taking up a whole lot of room where it is right now. So now if we say that this is now on the floor, because another issue is that if we use these cutters, these disc cutters, like I'm saying, is that we need a lot more vertical. We need a lot more vertical clearance than we need. We need a lot more. So we're not going to be able to get that to work with this sitting on the table. So we're going to take this space. So basically there's this cabinet, and then there's that table that I'm talking about. And then there's this cabinet area there where this, and then the cabinet ends, and then there's some room before the wall. And then again, usually we store sheets there. And that room is basically 4. So I just measured that now. That is 4 feet wide. So that's from the cabinet to the wall. And again, this is for also possibly an enclosure as well. It's got to fit in this area. And then to the front of the cabinet is 29, so 4 feet wide, or 48 inches wide. And then to the wall, the depth is 29 inches depth. So 48 inches wide, 29 inch depth. And then the height obviously could go all the way up to the ceilings, which they're like 10-foot ceilings or whatever in there. So, and obviously we're not going to go 10 feet up to the ceiling, but we have that room to do that. And really, the height on a VMC doesn't really affect it too much. Obviously, it depends if you're machining higher up. The higher up you go, the more you're going to have issues of bending, obviously, with moment. But if you're cutting, so let's say that you have a 40-inch Z versus a 20-inch Z, and you're cutting at 10 inches on both the 40-inch Z and the 20-inch Z, you're cutting at a 10-inch Z height, they're both going to perform identical. So obviously you're going to have more bending moment if you're cutting at a 40-inch height maxed out on your machine versus a 20-inch height on a different machine. So that's just going to be how it goes. So those are the types of things that we're looking at. And then obviously the idea with that is that it's going to be is that we're going to probably get half of those travels, if not less. So the idea is that with a 4 foot wide, 29 inch long, we're going to have, and again, we could go really, really far to the extents as long as these these blocks could hold the table up. And as long as the table's not crazy heavy, we could get it to where it goes all the way and bottoms out. And the idea is that these motors is that we have a lot of Z, but we don't have a lot of the other travels. So storing the motors inside other things is going to be where we're going to get our most bang for the buck. So storing the motors inside of the tables, or inside of other parts of the frame, so that we could get the most out of our travels and also make everything nice and tight. So again, 4 feet wide, 29 inches long. Chances are we're going to get half of that or less. So we're talking now, talking 48. So let's say 4 feet wide. So we would get because again, basically the reason why I'm saying this is that it'll go and hit something. So and again, also I could change this. So if we move the sheet out of the way and we move it to the other side, then we can make this bigger. So right now this is just temporary. It might change in the future. It's 4 feet wide, 29 inches long. So we're talking 14 and a half long by 24 wide. So that is even bigger than the Tormach. The Tormach 1100 is 10 and a half by 18 or something like that. I don't know what their new MX series is, so let's take a look at, or their new M series is. The servos are here. Okay. Okay, so technical specs. Alright, travels 18 inches by 11 inches. So they up the travel just a little bit, and then they have a 16 and a half. So we're talking about another 3 inches, another 4 inches on the Y. But obviously we're going to lose some because of the post of the machine. We're going to lose some, but also we could kind of stick out a little bit into the room. This is at the very end, but we don't necessarily need to do that. So we could also not do that. So we'll look into it. So here we go. But obviously, if this was not where this was moving, then we would get that whole thing. So this thing would be 48 inches wide by 29 inches long, which is size of some very big, industrial grade CNC machines, right? And then obviously you can see that in this housing, that's kind of the same deal. And if we look at the outside of this machine, and here's the table size, 34 inches. Obviously we don't need it that big, because the 34 inches, we're going to basically be hitting something. So we might make it bigger on one side and then worry about the sheets later, or we could possibly increase that. I'd rather want to increase the depth to make it close to square, because you're talking 14 and a half by 24. So I'd like to increase it by another 8 inches, but obviously if I do that, I need to increase it by another 16 inches to make it square. It needs to be 48 inches by 48 inches to be square, and we need another 19 inches. So that's not gonna help. Anyways, so yeah, so it's very, very similar to the size of the 1100 Tormach, but it's built with cost in mind, not 11 grand with. And then these they do have rails, so it's a lot, very, very similar. I mean, mine probably won't start out with bellows, with like these little fabric bellows or whatever like these do. And then whether or not we could get the ATC working. So let's look at a power head. Let's look at that power head again. And let's look at like a BT40. And so these are 4 horsepower, which is basically what that what's it called motor is. chainsaw. And so yeah, you see it's got a drive. It does have a drive bar in it, and obviously we have to, you know, weld something to this guy that basically allows it to stop at some point, to pull it in and stop. Actually, that might be what this is. And so here, I like this. It's got a lot of dimensions here. Probably talk to this guy more about it, but BT40. Okay, so this, and then this is for like a pulley or whatever. But it looks like this is just there, so we have to have something that stops it there. But yeah, this looks really, really nice. So maximum of 4 horsepower. So obviously that's way more than Tormach. Tormach's got a, I think this is now a 2 horsepower. Yeah, it's 2 horsepower now. So if I could give it that 2.5 horsepower spindle from the chainsaw motor, which I believe is stepped down. So here we could also step down and run off 0.01 millimeter. So again, this has a high runoff, but we're talking, you know, $300, $400 for the power head, and then basically a free, you know, free chainsaw motor. And we can see that here, this thing is not cantilevered too far. It's basically, it almost starts immediately, which is what I like. That's the big issue with the Skyfire, is that it sticks out so far with the Skyfire. And so here the total length is 300. 300. Stand by. Is 300. 361. 361. It's about 14 inches. So we need about 14 inches there of clearance, plus the head that pops out of it. So, but very interesting. We could get higher power out of it. Centering height. I think that's this. I don't know what that is. Anyways, or that might be height, just center. No. Anyways, rising temperature within 25°C, maximum RPM 6,000. So very similar to the Tormach. Let's see, what is Tormach now? 7,500. So very, very close to Tormach. Maybe higher horsepower, slightly slower spindle speed. We might be able to get the ones with the higher bearings in it, the higher speed bearings. But this will be definitely way more rigid. And does this one have... What does this have? Yeah, it's still an R8. And this is obviously BT40, which is way better than the R8, call it. So this is definitely way better. Obviously the run out, that's an issue. So run out here. Typical system footprint, 69 inches by 56 and a half. That's strange that it won't show the tolerances of like the run out and stuff. Typical system weight, so that's about 1,700 pounds. So obviously we would want something similar, but not, it doesn't have to be that heavy. We make it out of steel and we put the structure where it needs to be. We should be okay. So, and then obviously that. So we'll have something similar to probably this when we're done. I need at least a chip tray, and then maybe do a housing. So maybe something like this when we're done. So maybe a $20,000 mill for maybe $1,500 or something. So 48 inches wide, 29 inch depth. We're gonna get pretty close to what they got. minus maybe a little bit in the Y, which I'm a little bit disappointed about. Okay, so now basically why I have this guy open is let's look at some of the other details here. So this guy will probably be again, because now everything is going to be cut vertically. I now have the ability to go to my ex-boss's shop, and he wants to help me out with machining these things. So he has a what's it called? It's called a 18. It's called a 5T18. So it's an 18 piece tool changer 5T from Excel. It's a machining VMC. It's got like a 10 horsepower spindle, 8,000 RPM. Really nice. And it's like a 20 by 18 bed or something. So I could start machining these, and then in the meantime I could get this ready for the house and or shop later on to have inside of the garage, so that I don't have to go down to the machine shop to do some of this stuff. So that way I can work on my car or other projects or assemblies or whatever, and have welders and all my other stuff running at one time. So I could supervise the machine running as well as build my other stuff and have my laser running and all that kind of jazz. So he has Kurt vices. I don't think this is the exact vice that he has, but I'm pretty sure his opens up to a maximum of 9 inches. But it could open up even further if we have it on the top. If we have it go... wow, this is really small. Okay, so I think that's this here, DD. Yeah, DD is maximum. With jaws on the back of stationary and mobile jaw, which is DD. So DD is 16 inches, and what is regular? AA is 9 inches. So DD is 16 inches. So you could get almost maximum of a 16-inch pillar. So the reason why I'm looking at that is that we have to have a piece that goes into that to basically stabilize it. So the idea is that now we could go with a 19-inch column. Now my idea is for the column that we minimize weight but maximize rigidity is to run with a standard box frame column, or we do an I-beam column. So with that, I'll probably go with a 9-inch by a 9-inch column, so that we could get it nice and flat on there on the inside. Because again, these things are matched. If you read up here, they're body height matched. I believe this is what that's talking about, is on the tops here. So if this is super spread out and then this one's taller by 5 thou, this is taller by 5 thou, worst case scenario, or lower than 5 thou, then we have a tilt and we're not going to get perfectly straight. And we're going to see this in our machine. And so basically we're going to put the columns in here, which we have one column vertical, one column horizontal, and we're going to machine them flat. So we're going to have this column go in there, and then we're going to machine it flat, and then we are going to basically machine it flat on all edges, and then we're going to drill and put a really long rail on there, a really long carriage with two carriages each, pretty beefy carriage, as beefy as we could put on there, and then put another beefy carriage on there, and then basically have that attached. And then we bolt the two pillars together perfectly perpendicular to each other, so we need to make sure that the bottom is square, as well as so that's another thing, to be able to square the bottom up. To be able to fly cut it is going to be another issue on how we're going to square it up so that everything is nice. So again, a lot of this stuff I could talk to my ex-boss on how to go about it. I mean, I do have a pretty good understanding of a lot of it, but just to get some of these stuff, for example, 9 inches, that's a really long cutter to go down there and machine that. So Maybe we could put a stop on it, and then so every time we turn it, it's going to turn into the side that has the stop touching. So we basically machine a side, we set up a stop, we touch off of that side, and then we just kind of move forward from there. So basically to perfectly square it up. Alright, so that is the idea. So we have Fusion open, so we could look at a few different things. Number one is, let's go ahead and open up the, let me see, do I even have that? Do I even have that one yet? We have 10 minutes. My cat's kind of freaking out over there. DIY mill. Oh, this is an old one. It's the old one. So let's look up green. Let's do green machine mill. All right, so let's take a look at some of, and then obviously pretty much all of this is going to be steel, because again this is sitting on the floor, so we're not worried about any sort of issues with the table. So let's go ahead and do a rectangle and tighter. Cat's getting antsy. So 9 inches by 9 inches, let's say. And then let's do an offset. So let's close this. Offset. Let's say that this is like a ½ inch thickness or so, minus 0.5. We can even go more, but let's just try this. So now the question is, how are these going to mount? So we have the vertical come up, so is the vertical going to go on top of the bottom? Or is the bottom going to butt up to the vertical? Right? I don't think it really matters much. Either way, I think will work pretty well. So let's just say that the bottom is going to hit there. So again, we have this guy here is going to be 36 inches. 14 inches. So we need at least 14 inches plus. I would like the spindle to clear the all our parts, and the biggest part I would probably ever put on there is 12 inches tall, plus the vise. So what's the bottom of the vise? Let's say. Well, let's just go with Tormach. So let's see what Tormach's got, and we'll just beat kind of Tormach's thing. Tiger, quiet. My cat gets really nervous when I start talking. So spindle nose to table clearance, max clearance. So 17 inches. So let's say that. So 17 inches spindle to table clearance plus 14 inches. Let's say 15 inches. So 17 plus 15. 17. And then this goes where? This goes all the way to the end of... Oh, but this does not go to the end of where the drive dogs are. So the drive dogs are even taller. Okay. Alright, well, if that's the case, then yeah, so let's say 15 inches. Let's give it another ½ an inch there, right? Yeah, well, let's give it another 0.8 inches, which is probably as tall as the drive dogs are. Okay, so let's say that. Let's say 15 inches plus 17 inches, so 7, 8, 9, 10, 11, 12. So that's 22 inches. So let's say that 22 inches plus the, let's say that this is sitting on top. So let's just do 22 inches for right now. 22 inches. And there it is. All right, so now let's look at my bodies here. Physical material. And let's say that this is a metal. That this is, ooh, what the heck? Let's say this is regular A36 steel. A36 at the end, yeah, it is regular A36. Okay, so now we have A36 here. What is the weight that we're already looking at? Properties. 0.1697. Whoa, that's already divided by 16 pounds. We're already talking 100 pounds right there for a 22-inch piece of steel that is this thick. Obviously, these ends are rounded, so there is that, but mass. "22-inch beam." That's pretty big. Okay, so now we're talking. We're in good shape here. So let's call this the Z column. Okay, so now let's do File, New Design. Let's call this the Y column. Yeah, Y column. Okay, so let's do the same deal here. Let's say it's a 9x9. Nine by 9 offset. Even that I think is pretty low in weight. I personally think we should have at least 100 pounds per column or more. This was 1697 divided by 16. Obviously, it's going to be hard to move this around. Okay, so it's 100 pounds. So it's, at some point, it's going to be hard to put in and put out of the machine, and we need a crane. So obviously, we can't go past that point. And then so now this one, basically that column's sitting on top, so we have 9 inches plus our maximum, which is 29 inches. So let's go ahead and do that. So this is 9 inches plus 29 inches. Now this is going to be a heavy sucker here. So this guy, and again, so that's why I'm kind of thinking I-beam, is that we could have more rigidity as far as like twisting and stuff, because we have it's probably going to be lighter. But we'll have to see. We'll look at that on another, on one of the next videos. So again, because I already kind of have a machine to do this with, just not at home, and I would like to, get a few of those established. This video is probably going to be only once a day, maybe between this one and the router. So. Okay, so now this is going to be heavy. This is going to be, whoa, 2,931 divided by 16. So almost 200 pounds. So it's almost my weight getting that thing up into the CNC machine, which obviously is in an enclosure. So that's also going to be hard. So this might be something that we just stick on a regular mill, and then we could use like a forklift to lift it on there or something. Or I mean, even this with this, we could use like a cherry picker also. Go rent a cherry picker, and then with that, because it's not that tall, so we could get the cherry picker with a short chain and be able to get it inside the machine. So that's interesting. So Y column, let's save that. Z column, we got that. So now let's look at kind of what already. So let's call it layout, and let's do another one. Okay, Tiger. Let's call this one general layout. Okay, so now let's go back. And let's do Z column, Y column, and then let's go ahead and joint it. And then obviously the idea is that we have this and as much space as possible, basically, or even welded. We might bolt or weld this together. Okay, so yeah, that's basically what it's gonna look like. And so let's go and hide the joints. So there, this one is the 22 inches. So this is the 22 inches, and then this is the other one. But now the question is, can we actually clear that? So again, the other idea is that because it's a VMC, basically this spindle has to reach out to the middle. And so the idea is here that another thing is I'm going to put the motor out here so it holds it into the cut, right? So it holds it down and helps hold it into the cut, so it doesn't lift up. So basically it has to tilt that whole entire thing in order to lift it out of the cut. So I get a little bit more moment inside of the cut. Either that, or I might put it, it'd probably be, this is going to be really, really close to the gantry anyway. So let's see. So we need it needs to cantilever basically out almost 14 inches, which is a ways. So let's see here. This is only 60 millimeters, which we only have 2.3 inches. So we're already in some pretty deep trouble, because that's only going to give us a very small amount of travel. So basically we're going to have to lift that out almost 14 and a half. So about 14 and a half inches minus 2.5. So 14.5 minus 2.5. I don't think you can do minus on here. So let's just say 12. 12 inches is 304.8 millimeters. So that's kind of how they're getting this thing, I think, cantilevered out so far, is to get the travel that is necessary to get that spindle to be right in the middle of the table. So let's go ahead and let's do one more thing. We're already over time, but let's do this. So let's call this spindle, so let's call this, call it spindle head test. So now what we'll do is we'll just make it like this and like this. Let's do center rectangle. And now basically what this has to be is this is going to be this guy. Oops. This guy, which is 135 millimeters wide. Wait a second. Yeah, 135 millimeters wide, which is a good 5 inches. So also we're going to lose that. Actually, no, we won't lose that. That doesn't matter on the Y. It's just, yeah, because it's in the center point. This spindle's in the center, so it doesn't really matter. So 5.3. So let's say that this is 5.3, and that this is, what was it? 12 inches. Well, it's actually what, 14.5 plus, then we have this other piece here, plus 122. And there we go. Oops. There we go. And then basically this is now 361 inches tall. 361 millimeters. 361 millimeters. Okay, so now that's basically the spindle. So let's go ahead and save that, and then we'll just kind of drop that in to see what it looks like. And again, this guy could stick up. You know, it just kind of matters that basically the points that we're attaching are right here and right here. So technically this is only 160, it's actually only 160 millimeters tall. 160 millimeters tall. Right, which is probably why they have that column so tall. I mean, that thing's taking up 61 inches. This thing's taking up like average height. So it says 92 inches tall, so it's about 8 feet tall. So that's obviously, I'm assuming, with the table. So let's say that it's, at least it has like a 3 feet table on it, just to get it up to where it's starting at. Let's say maybe even 4 foot table. Yeah, let's say 3.5 foot table. So 3.5 times 12, that's 42, and then let's make it negative, so that's overall system height. So you're talking 50 inches tall, to where the spindle pops out to the top. So right now we only have 22 inches. So right now, if we do the same thing, 3.5 feet times 12 plus 22 inches, we're at 64 instead of 92, so we would have another 38 inches. We could probably do this, guys, so we could add another 38 inches and make this thing really beefy, but obviously we got a tiny little spindle head just like this, and he's just basically got the motor on top. But what that allows us to do is keep the sort of the tilting at bay, because again, this thing's got to stick out a long ways. So, all right, that's basically it for this video. So thank you for tuning in for this video. I'll see you guys in the next one tomorrow. I'll catch you guys later. Thanks for watching. This is Steven from Legit Tech Tutorials and the Green Engineers. I'll see you guys next video. Take it easy. Peace.